Today, let's review some of the problems in the practice test here. I want you to be able to do not just these specific problems, but problems similar to these. For instance, on the first example, you see that you revolve this around the x-axis and find the volume. I'd like you to be able to revolve a little bit around the y-axis and find the volume. I'd like you to be able to use similar methods, like this is the area, this is the method of discs. When you revolve this, the cross-section are discs. Be able to do washers, be able to do cylinders, be able to do general cross-sections of area A of X. Those are the four methods we had for finding volumes of solids this semester. So let's try this first one. If I revolve the shaded plane region below y equals square root 4 minus x between 0 and 4, it revolves to sort of a bullet-shaped solid like that, and I observe that the cross-sections are discs. Right? So I take the radius r of x at the point x along the x-axis, and I say, oh, that's just the height of the function, square root 4 minus x squared. And the method of disc says that the volume of the integral from a to b of pi times the radius squared dx. It's really just the area of the typical cross-section at x. The method of disc is just a special case of that. So is the method of washers. So we can pull the pi out and integrate from 0 to 4 is where the cross-sections begin and end. R of x dx, where r of x is square root 4 minus x squared. R of x squared, it is. So integral a to b pi r of x squared dx. All I have to do is integrate 4 minus x squared with respect to x. Well, that's 4x minus x cubed over 3. Put in 0 and 4. I'll let you finish that. Right. So there's an example of the method of discs. Be able to do the other methods and revolve around the other axes. Let's try number 2. Number 2 is finding arc length. That's another thing we learned, right? How can I find the arc length of a curve? There's a formula for that. Suppose y equals 3x to the 3 halves minus 1 is the plane curve. And it goes from x equals 0 to x equals 4. Revolved around, not revolved. The arc length formula was the integral from a to b, square root 1 plus dy dx squared dx. You need to be able to do this. Alright, so this is the integral. The curve starts at 0, let's see, 0 and ends at 4. And dy dx, the derivative of this is 3 times 3 halves, x to the 1 half is 9 halves x. And then I need to square that. So this is the integral from 0 to 4 of the square root, oops, 9 halves square root x that was, is the derivative. 1 plus 81/4 x dx. Now when you see a function of a function, a big hint is to think about what would happen if I let u be the inside function. 1 plus 81/4 x in this case. Then du would be the derivative of that dx, right? It's du dx would be 81/4 dx. Consequently, dx would be 4 over 81 times du. So I'll make that substitution in here, rewrite this integral. When x equals 0, u is 1 plus 0 is 1. When x is 4, u is 1 plus 81 is 82. And now this becomes square root of u, or u to the 1 half. du gives us the 2/3 u to the 3 halves. U evaluate at 82 and 1 and take the difference. All right, let's try number 3 now. Find the surface area generated by a curve. So you take this curve between x equals 0 and x equals 1. It looks like this. What does this look like? If you square both sides, you get y squared equals 9 minus x squared, which says that x squared plus y squared equals 9. This is a circle of radius 3 that you're revolving. And suppose I revolve that between x equals 0 and x equals 1. I just get this piece of a sphere between here and here. And here's the surface area I'm finding. Well, the formula for surface area now is integral from a to b, 2 pi f of x, square root 1 plus f prime of x, or dy dx squared, dx. All right, so you just have to be able to evaluate this. Well, the surface, the curve that you did at the beginning, the arc of the circle, y equals square root 9 minus x squared. Started at x equals 0 and finished at x equals 1, so we'll integrate from 0 to 1. Let's pull the 2 pi out just for convenience. F of x is then square root 9 minus x squared, and this is square root 1 plus derivative of this. Well, we need to compute it somewhere. Y prime is the derivative of 9 minus x squared to the 1 half. Is 1 half 9 minus x squared to the minus 1 half times the derivative of 9 minus x squared is minus 2x. The 2's canceling gives us minus x over square root 9 minus x squared. So this is minus x over square root 9 minus x squared. Now this is a little trickier integral until you realize it has to be a Cook's problem. What can the trick be? Well, let's see. This is square root 9 minus x squared, square root of 1 plus, I forgot my square on here, 1 plus x squared over 9 minus x squared. And now this is 9 minus x squared over 9 minus x squared here. So I replace the 1 with that. And the x squareds cancel. Now it's a little better. This is 2 pi integral from 0 to 1 square root 9 minus x squared, square root of 9 over 9 minus x squared dx. And now this one cancels this one. Square root of 9 is 3. What I have is 6 pi integral from 0 to 1 dx is just 6 pi. All right, we ran into hyperbolic trig functions. Let's try computing a hyperbolic tangent of the natural logarithm of 2 exactly by hand. Some calculators can check this. I would like you to show your steps on the test. I may add for those, ask for those. Oh, you just have to remember that hyperbolic tangent, what is it? Well, if you remember sinh and cosh, right, then you can remember hyperbolic tangent. Hyperbolic tangent is sinh over cosh. And sinh was e to the x plus e to the minus x over 2 minus, and cosh was e to the x plus e to the minus x over 2. The 2's cancel. It must be that hyperbolic tangent is e to the x minus e to the minus x over e to the x plus e to the minus x. But x replaced by ln2. So it's e to the ln2 minus e to the minus ln2 over the same on the bottom with plus. And then minus ln2, you think of it as minus 1 ln2 is ln of 2 to the minus 1. So this is e to the ln2 minus e to the ln of 2 to the minus 1 over e to the ln 2 just by properties of logarithm. E and ln undo each other, so e to the ln of 2 is 2, e to the ln of 2 to the minus 1 is 2 to the minus 1, or a half. And you have, let's see, 3 halves over 5 halves is 3 fifths for this one. Suppose you want to evaluate an integral by substitution. Again, that rule applies that if you see a function of a function, try thinking of u equals the inside function, in this case minus 2x cubed. So to evaluate x squared e to the minus 2x cubed, recall I try u equal this, then du has to be the derivative times dx of minus 6x squared. dx, that's a multiple of what I have here. I can rewrite this as minus a 6 du to replace x squared dx. So I scratch out x squared dx and put it minus a 6 du. I scratch out e to the mass and write e to the u. And what I have is minus 1/6 integral e to the u du. Since e to the u is its own antiderivative, which is minus 1/6 e to the u plus a constant, or minus a 6 e to the minus 2x cubed plus a constant. There's number 4. 5. Alright. Let's try finding the derivative of a hyperbolic trig function. Alright. The idea is that you want to be able to do the integrals and derivatives. I said before, you don't want to memorize all these hyperbolic trig things. They aren't used as much as the ordinary trig functions. But I have your table available. I may ask you some of these things. You do want to know the few fundamental identities that cos squared minus sinh squared equals 1, and derivative of sinh is cos, derivative of cos is sinh. If you know those, you can figure the others out. They're similar to what you do with trig equations. So let's try this one. What is the derivative with respect to x of hyperbolic sine of x squared over 2? Right? Well, you put u equal x squared over 2. This becomes d dx of sinh u is d sinh u dx. And you put these canceling du's in here, and it's the chain rule. Right? So d sinh u du dx. Derivative of sinh is cos. Derivative of 1/2 x squared is x. Alright, so this is x hyperbolic cosine of x squared over 2. Then we have a whole bunch of integrals to evaluate. Suppose I wanted to integrate 0 to pi over 4 sine cubed of 2x cosine fifth of 2x dx. The big trick is to recognize when you have a power of sine times a power of cosine, if one of those powers is odd, you're going to let u be the other function. So if this power is odd, and it is, I'm going to let u equal cosine. Since this power is odd, I can also let u equal sine, and either one will work. So let's let u equal cosine. Then du is the derivative of that dx, well, let's write it out, du dx dx, I like to write this, is derivative of cosine is minus the sine, derivative of cosine 2x is minus 2 times the sine. Right? Remember the derivative of cosine kx is minus k sine kx in general. So we need one of these signs to become part of my du. Let's rewrite this as integral from 0 to pi over 4. And I'll take one of those out and leave a sine squared 2x. Cosine to the fifth 2x. And then I can put a minus 1/2 and a minus 2 sine 2x dx. And now it's the same thing, right? Sine squared times sine is sine cubed. 2 times 1/2 is 1 minus and minus cancel, as I've just got sine cubed cosine of the fifth dx, just like I did before, but now this becomes du. This is 1 minus cosine squared, right? Sine squared is 1 minus cosine squared, is 1 minus u squared. Cosine to the fifth is u to the fifth. And I have this integration. Now the endpoints have to change, or I can switch back to x at the end and put these numbers in. If I change them, suppose u equals cosine 2x, then cosine of 0 is 1. Cosine of 2 times pi over 4 is cosine of pi over 2 is 0. So now the integral goes from 1 to 0. Well, I can take the minus off here. If I switch the order of integration and go 0 to 1, I get minus the integral. Then that'll cancel this minus here. And I can rewrite this as plus 1/2 outside. Integral 1 minus u squared, u to the fifth, du. Well, let's see. This is integral of u to the fifth minus u to the seventh. So it's u to the sixth over 6 minus u to the eighth over 8. Plug in 0 and 1 and take the difference. You've got 1/2 of 6 minus an eighth. Hope you can still see this on the camera. Let's see. That's 4 24ths minus 3 24ths is 1 24th. I guess this all comes out to 1/48. Yeah. Next one, there's two ways to do it. One is just multiply out and use partial fractions. That works. Or even without multiplying out and use partial fractions. It might be easier though to integrate x squared over x minus 2 squared dx by substitution. Let u equal x minus 2, then du is du dx dx is just dx. So I replace this with du. And if u is x minus 2, then x equals u plus 2. So I can write this as the integral x plus 2 squared, u plus 2 squared over u squared du is now the integral of u squared plus 4u plus 4 over u squared du is integral of 1 plus 4 over u plus 4 over u squared. Comes out to be u plus 4 natural log absolute value of u minus, well, plus 4 times the integral of u to the minus 2, which is u to the minus 1 over minus 1. So I just get minus 4 over u plus a constant. Comes out to be, let's see, x minus 2 plus 4 natural log absolute value of x minus 2 minus 4 over x minus 2 plus a constant. So either way you like to do that one. We have this integration technique. If you see a square root of x squared minus a squared, or a square root of a squared minus x squared, or a square root of a squared plus x squared in an integral, a hint is to try a trig substitution. So part C here, I can integrate x squared over square root x squared minus 4. And when you have x squared minus a squared, the trick is to let x equal a. If you think of this as a squared, this is a. X equals a secant theta. And then this becomes 2 secant theta squared over square root 2 secant theta squared minus 4. And if x is 2 secant theta, then dx is its derivative, 2 secant tangent d theta. And so here we have 2 secant tangent d theta. Well, now there's a trick that goes on. what you do is you can try and draw a triangle, a right triangle to go with this, where theta is the angle, and if x equals 2 secant theta, then you have x over 2 equals secant theta. Secant is the hypotenuse over the adjacent, so the hypotenuse could be x and the adjacent could be 2. And I can make this triangle, and then this side would be the square root of hypotenuse squared minus adjacent squared is x squared minus 4, which is precisely what I have in the integral. And let's see. This comes out to be 4 times 2 is 8. Integral secant squared times secant is secant cubed. Tangent theta over what is square root x squared minus 4. If you think about it from the triangle, instead of making this substitution, which does work if you then remember one of your Pythagorean identities, you can instead say that, well, square root x squared minus 4 over 2 is the tangent of theta. So for this is opposite over adjacent is tangent. So 2 tangent theta could replace square root x squared minus 4. Alright, so this is 2 tangent theta. I left off my d theta, there we go. So secant cubed, 2 squared times 2 is 8, and the denominator becomes 2 tangent theta. Alright, now the tangents cancel. I just have to integrate 4 times integral secant cubed theta, d theta. Well, there's a trick for integrating these also. If you see secant to an even power, unfortunately it's not, you can substitute u equals tangent. If you do tangent to an odd power, you can substitute u equals secant, unfortunately not. But there is a reduction formula, so I would use the reduction formula in this case. Well, this next example is to remind you that when you see a small power of x times a trig function, a hyperbolic trig function, a logarithm, or an exponential or some other functions, you can think of using integration by parts, because if you let u be this part and dv has to include the dx be the rest, then u equals x squared, dv equals sine 2x dx. Du is the derivative of this dx, is 2x dx, and the power comes down. V is the integral of this one, is 1/2 minus 1/2 cosine 2x, plus a constant. You can leave out the constant integration by parts. So we'll rewrite this as uv minus integral v du. Right? So it's x squared times minus 1/2 cosine 2x minus integral minus 1/2 cosine 2x times 2x dx. So the minuses cancel and the 1/2 cancels the 2. We've now got minus 1/2 x squared cosine 2x plus the integral of x cosine 2x dx. And it looks about the same as this one, except instead of sine you have cosine, but you've reduced the power of x squared to x to the first. So now you can substitute, do integration by parts again, letting u be this part and let dv be the rest. Then du is the derivative of this dx, it's just dx, 1 dx. And v is the integral of cosine 2x, is 1/2 sine 2x. And now if I rewrite this as u, this part, plus uv minus integral v du, the integration by parts formula, we should get minus 1/2 x squared cosine 2x plus, let's see, x times 1/2 sine 2x minus integral 1/2 sine 2x dx. This is an easy one to do. Another kind of integral you can think of using integration by parts on are integrations involving logarithms and inverse trig functions. For instance, suppose I just want to integrate natural log of x. I could let, well, so if I let this be du, then define, or dv, then to find v, I have to integrate this, but if I could integrate that, it would already be done, so that can't be dv. dv has to include this part, so the only thing I can do is pick that equal dv. That leaves this for u. And now if u is ln of x and dv is dx, then u is du dx dx is 1 over x dx. And v is the integral dx is x. So this is uv minus integral v du. Again, you can leave off the constant when calculating v in integration by parts. This is u ln x times v is x minus integral v du, that should have been 1 over x dx. So it's just x ln of x minus integral of 1 is x. We have x ln x minus x plus a constant. Gives us this integral. How about the next one? This looks pretty similar to this one, doesn't it? Integral x cubed over square root 4 minus x squared. What do I do when I see a square root x squared minus a squared or a squared minus x squared? I make the substitution. This time it's square root a squared minus x squared, so I'm going to substitute x equals a sine theta. And then dx, is the derivative, is 2 cosine theta d theta. And if you draw your triangle again, and say putting the angle theta in a right triangle, if you want x to be 2 sine theta, then sine theta is x over 2. We could put x and 2 like this to make it so. Now this side has to be square root of hypotenuse squared minus leg squared. Oh, look at that, that's the bottom. So now we observe from that cosine theta equals adjacent over hypotenuse twice the cosine theta can replace the square root that I see in there. Or you can use the Pythagorean identities from trig to replace this. So I'll replace this one with 2 cosine theta. If x is 2 sine theta, then dx is this derivative d theta, is 2 cosine theta d theta. And x cubed, then I have to replace with 8 sine cubed. So this becomes just 8 times the integral of sine cubed over 2 times cosine times 2 times sine. Oops. 2 cosine d theta. Alright. So there we go. The 2's cancel. And what we've got is integral 8 times the integral of sine cubed theta d theta. This time we don't have to go to a reduction formula. We can look at this and say, well, if we rewrite it, since sine is odd, we can substitute u equal cosine. Think that this is sine to the third times cosine to the 0, product of power of sine and power of cosine. Let u equal sine. Then du equals cosine theta d theta. This integral rewritten as sine squared. Whoops. Since sine power is odd, I want to let u equal to cosine. And then du is minus the sine of theta d theta. And we'll write this as sine squared, or 1 minus cosine squared, times sine theta d theta. Right? So there's sine squared times sine is sine cubed. But now u can replace cosine, so this becomes u squared. Du can replace minus sine theta d theta, so this becomes minus du. And I have minus 8 times the integral, well actually let's put the minus in here, call it 8 times the integral of u squared minus 1 du. Distributing this minus to these terms. Alright, and then finish that one up. How about the last one there? Lots of integrations, huh? I want to integrate from minus infinity to infinity. We call that an improper integral. Not only do I have an improper integral, I've got a big time denominator here. What do I do with this? You can try partial fractions on some of these things. When do you use partial fractions and when do you use something else? Well, if you look at this, a quadratic ax squared plus bx plus c is irreducible if b squared minus 4ac is negative, in which case you can't factor this any further, so this already is the partial fractions decomposition. Let's see. B squared is 4 minus 4 times a times c. It's negative. This is already the partial fractions decomposition. So instead of, realizing that, I realized that I can evaluate this thing by completing the square. When you have an irreducible quadratic, you rewrite it, oops, it's x squared, sorry. As a perfect square, x squared plus 2x plus 1/2 of this number squared is 1. And that leaves 1 left over here. And now this is the integral from minus infinity to infinity of 1 over x plus 1 squared plus 1. So just the substitution, u equals x plus 1, in which case du is the derivative of dx, it's just dx. And this becomes u, this becomes du, and as x goes from minus infinity to infinity, so does u, so this becomes the integral from minus infinity to infinity of 1 over u squared plus 1 du. This should look familiar, right? The antiderivative here is arctangent. So this is just arctangent of x, of u, taken from minus infinity to infinity. Technically, if I write out all the details, this is arctangent b minus arctangent a. Limit is a goes to minus infinity, b goes to infinity. I'll just write it like this for short. As u goes to infinity, arctangent of u, maybe you remember the graph, right? Looks like this. As an horizontal asymptote, pi over 2, the definition of asymptote is that the limit is this number, pi over 2. Then we subtract the bottom point whose limit is minus pi over 2, right? As x goes to minus infinity, as u goes to minus infinity. And so pi over 2 minus a minus pi over 2, this actually integrates the pi. On this one, the instructions were on the other page. It says, complete the square, make a substitution, and evaluate the integral. Suppose I want to evaluate x over the square root of 20 plus 4x plus x squared. These things are liable to be in your table at the end paper of your book and also on your calculator, so you should check your answers with this, but I want to see the work on the test. But you can check these answers. Suppose I try and complete the squaring here. That's similar to the last example. I could say that to complete the square, I take 1/2 of this and square it. So I'll rewrite this as x over square root 4, 1/2 of this squared, plus 4x plus x squared. And then that, I need 16 more, so that I don't change the argument of the square root. Well, this is now x over square root of 4 squared plus x plus 2 squared dx. If you make a substitution, u equals x plus 2. replace the top with u minus 2. I replace dx with du. I replace x plus 2 with u. This whole thing comes out to be the integral of u minus 2 over the square root of u squared plus 4 squared du. And maybe you remember when you have x squared plus a squared or u squared plus a squared, the proper substitution here is to let u equal to tangent theta. And this one will reduce this integral nicely. Du being 2 secant squared theta d theta. And you can draw the triangle this time. If you want u to be 2 tangent theta, then tangent is u over 2, so I can put u here and 2 here, theta in my right triangle, and then this is square root u squared, oops, this has been 4. Proper substitution, u equals a tangent theta is 4 tangent theta. This becomes 4 secant squared theta, and we have sides 4 and u squared plus 4 squared square root for this side. This will make this one work. How about differential equations? If I say state the order, that's just the highest derivative that appears, so it's first order. That's its first derivative. Confirm that the functions of the given family are solution. That just means plug in y equals c plus x. C times 1 plus x, and then dy dx is its derivative, is in c. You put those into the differential equation and get, by plugging in, on the left, 1 plus x times dy dx is c, is equal to c times 1 plus x is what y was. And sure enough, plug in dy dx on the left side, you get the expression on the right side, and that shows us the solution. Every element in that family, regardless of c. How about finding the solution of each initial value problem? We only have 2 methods to solve differential equations. One of them is separation of variables, and the other one is if the equation is linear. And so you ask yourself, is this linear? If you want to write it in standard form. If I have x dy dx plus y equals 2x, is that a linear equation? Well, you try and write it in the standard form, dy dx plus p of x, y equals q of, equals f of x. So I'll have to divide this through by x, dy dx plus 1 over xy equals 2. And sure enough, dy dx plus p of x equals f of x. When it can be written in this form, there is actually a formula for writing down the solution immediately, but it's easier just to remember that there's an integrating factor, e to the integral p of x dx, that you can multiply through this by to make it integrable. This is e to the integral 1 over x dx in this case, is e to the natural log absolute value of x, plus a constant if you want, but you don't need the constant, you want any integrating factor. So we'll choose c equals 0. Then this is absolute value of x. Well, technically, since we're only solving this for x greater than 0 or x less than 0, we can just use x as the integrating factor and forget the absolute value, and this works just as well. Technicality, you don't need the absolute value on this one. And so we'll multiply through by x, this one, and sure enough we get back what we started with. X dy dx plus y equals 2x. It was a trick, right? But now you notice that this original thing was actually already integrable. This, by multiplying through the standard form by the integrating factor, this always becomes a derivative of the product mu times y. It always has to be the derivative of mu, which in this case is x, times y. Let's check. Derivative of 1 times y, that's this one, plus x times derivative of y, that's this one. Sure enough, it's the derivative of the integrating factor times y. Just look for that product rule, is equal to 2x, and now you can integrate both sides. Integral to the left, integral of the derivative is x times y. Integral of 2x is x squared, and then there's an arbitrary constant you do have to put in it, you won't get all solutions. the general solution, we call it, is y equals x squared plus c over x. And now you can see why you didn't need, actually, the absolute value. It's only, the solution only occurs on, for x greater than 0 or x less than 0. Otherwise, you're going to divide by x in the middle where it doesn't satisfy the equation. And on x greater than 0 or x less than 0, this isn't an integrating factor because any multiple of an integrating factor is an integrating factor. And so the absolute value of x is x in the positive interval, absolute value of x is minus x in the negative interval. So it's the same integrating factor as x, really. Just multiply the equation through by minus is the difference. All right. Now, this one is separable. I gave you a hint here. Separable means that you can write the right-hand side when you have d dy dx on the left by itself. You can separate as a function of x times a function of y on the other side. So here's the differential equation separated, a function of x times a function of y. Now what I do is I try and get all the x's with dx on one side, all the y's with dy on the other. So I divide by 2y squared. Well, let's just divide by, divide by 2y squared. And then multiply by dx, and I get this equation. And we proved before that if you do that and slap an integral sign on there, then this is the solution set. And so now what's this one? This is twice the integral of y to the minus 2 dy equals integral 1 over x is natural log absolute value of x plus a constant, but we can leave it off because it's going to come out of this one anyway. Integral of y to the minus 2 is y to the minus 1 over minus 1, so we'll say minus 1 over y here. Now we'll put our constant on, and there's all solutions. We just have to solve this for y, so we'll take the reciprocal and say y over minus 2 equals 1 over natural log absolute value of x plus a constant. And then multiply by minus 2, y equals negative 2 over natural log absolute value of x plus a constant. If you're in doubt whether you got the right solution, if you have time, you can plug this back into the differential equation and see if it satisfies like you did in this first one. That's how you check your solution. Now, we haven't applied the initial condition in either case. Let's apply it on this one. I didn't finish the last problem, actually. Plugging in the initial condition determines the constant. If I have dy dx, y equals minus 2 over natural log x plus a constant like that. If I put in x equals 1 when y equals 4, then 1 goes in here, 4 goes in here, and I just have to solve this equation for c. So y of 1 equals 4 gives this. And now ln of 1 is 0, you remember. Natural log of 1. 4 equals minus 2 over c, so I multiply by c and divide by 4, and I get c equals minus 2 over 4 is minus a half. I put that in here and get the unique solution to the initial value problem, right? The differential equation has this infinite family of solutions, but when I apply the initial condition, only one comes out. It's y equals minus 2 over natural log x minus a half. Might be worth multiplying that through by 2 to make it a little simpler, or maybe by negative 2. Call this 4 over 1 minus 2 ln absolute value of x. Technically, we can drop this absolute value since this is the solution on an interval that includes x equals 1. X is always going to be positive, right? You can't take the logarithm of a negative number. If x is always, or of 0, if x is always going to be positive or negative in order for this to be a differentiable and satisfy the differential equation, we'll pick positive to include the initial condition. All right, so there's that one. Finally, if you use Euler's method here, with size delta x equals 0.25, this is just a plug and chug problem. Suppose I have number 11. Y prime equals x minus y of 0 equals 1. This is to show you that computers can approximate solutions to these things. So if you could evaluate this one using your techniques for solving differential equations, you could run the computer, get approximate points on the solutions, what this will give you. And the rule is that yn plus 1 equals yn plus delta x times f of xn yn at the n plus first step. And you just do this over and over. So you say, this is the algorithm. You're given x0 and y0, the initial point. Then for n equals 0, 1, 2, and so on, as many steps as you want till you cross your interval. Y is incremented like this. X is just incremented by the step size. And what step size do we want? We said, well, we want to solve it on 0 to 1 with step size 0.25. So apparently we do four steps to go from here to here. So you put n equals 0 into this algorithm. Put n equals 0, and you're given, this is x0 and this is y0, your initial point. Then we get y1 equals y0 plus delta x times f is this one. F is x minus y, so it's xn minus x0 minus y0 is this part. So y1 is this, but y0 is 1. Delta x we were given is 0.25. Just told me to use that. If it's not good enough, use a smaller step size and the answer gets better, remember. Let's see, x0 is 0, y0 is 1. So it's 1 minus 0.25, y1 is 0.75. Now x1 just increments x. It's x0 plus delta x is 0 plus 0.25 is 0.25. So we have our next point. Now we just keep, you are the machining. We go to the next step and say when n equals 1, I just don't have room to put this, do I? N equals 1, our algorithm says y2 equals y1 plus delta x times f was x minus y, so this is x1 minus y1. And let's see, that's 0.75 plus 0.25 times x1 minus y1 was 0.25 minus 0.75. Well, minus 0.5 times this is minus 0.125. It looks like I get 0.675. And then x2 is x1 plus delta x is 0.5. And there you've got your x2, y2. You do it 2 more times until you get x4 equals 1, and then you're done. On my last answer, I'm sorry, but y2 should have been 0.625, a little subtraction error there, so y2 equals 0.625 and x2 equals 0.5. Let's try the last one here. This is another differential equation problem. Suppose we have an initial population of 10,000 bacteria, grows exponentially at an instantaneous rate 1% per hour. This is an instantaneous rate, it's not actually 1% per hour, it's a little faster than that. So, what we're saying when we say it has an instantaneous growth rate of 1%, 1% is 0.01, so dy dx is 0.01y is what we're saying. 1% of y, instantaneous rate of increase. So that's what the statement translates at. And if initial population of bacteria, if you start at time 0, that says y of 0 equals 10,000. So there's a differential equation. And writes an initial value problem. That's this is A. We write down the differential equation for bacterial growth, which says the rate of growth is proportional to the population present. That's the bacterial growth model. Now let's find a formula for y of t. That means we have to integrate this. This is either linear or separable. You can use either method. Let's separate variables. dy over y equals 0.01 dx. Slap an integral on it. So we separate variables by dividing by y and multiplying by dx. Slap an integral on it, and this becomes then natural log absolute value of y equals 0.01 x plus a constant. Evidently y is equal to plus or minus e to the 0.01 x plus c. Well, e to the c is an arbitrary positive constant. Plus or minus makes it an arbitrary positive or negative constant, so we'll call this y equals p0, an arbitrary non-zero constant, e to the 0.01 x. But now, when we're way back here, when we divided through by y, we assumed it wasn't zero. If we check that solution that function y equals 0 separately, we see it actually does satisfy this, right? The derivative of 0 is 0 is equal to 0 on the right. So p0 actually can be positive, negative, or 0. So we can put that in here, that this is the case, or y equals 0 is the solution. And now here's all solutions. p0 is an arbitrary constant. Now you apply the initial condition, part C. This is the family of solutions. Oops. I guess I need to plug this in B also. So you plug in x equals 0, y equals 10 to the 4th, and you get 10 to the 4th equals p0 e to the 0, tells you that p0 equals 10 to the 4th. And evidently our unique solution to this initial value problem is y, the population, plus be 10 to the 4th e to the 0.01 t. When you start to see these, you begin to recognize this is the growth rate, this is the initial population. It's almost as easy to memorize a formula, maybe. So you should see this when you're all done. How long does it take for the initial bacteria population to double? Well, you can do this. You want to find t such that you got 2 times 10 to the 4th bacteria. So 2 times 10 to the 4th for y equals 10 to the 4th times e to the 0.01 t. And just solve for t. Divide by 10 to the 4th, you got 2 equals e to the 0.01 t. Now you can take the logarithm. When you have an equation with a variable and exponent, you solve it by separating the exponential on one side and taking the logarithm. Now we've got ln2 equals ln of e to the 0.01 t. ln and e undo each other. You've got ln2 equals 0.01 t. Multiplying by 100, I get t equals 100. Natural log of 2. Hope that helps. Try this, finishing these up and see if you have any questions.